Hello, everyone. I see that there are 8 people online right now, so I'll just wait a moment in case a few more people join. All right, well, um, thank you for being here. The plan for today is just to introduce myself and to explain a few aspects of Cricking, so just give you a very brief overview and then to show you a bit how the Variogram works, how you can implement it in code, and to give you a chance to ask questions about this since there's no homework assignment about this topic, and also since we moved all of the sessions online for the next 2 weeks, yeah, just to have some more interactivity in the course. Yeah, well, my name is Ken Arroyo Hori. I'm a lecturer and researcher at the 3D Information Group in Delft. I'm a colleague of Hugo and Ravi. My background is that I did a bachelor in computer science in Mexico, and then I moved to the Netherlands to do the master in geomatics. I continued there. I did my PhD there, also in the 3D Information Group. Then some postdocs, but since last month I'm officially only working part-time for TU Delft, so that gives me a chance to do a few other things. But I'm still very happy to be teaching this, and I will hopefully see you in the 3D modeling course in the next quarter, hopefully in person. So let's move on to the topic of today's lesson. Hopefully you had a chance to go through the course materials already, but just in case you didn't, we will be talking today about one spatial interpolation method, which is called Cricking. It is a bit different from the methods that you saw last week, because it's a bit more sophisticated. Like most other spatial interpolation methods are based on a pretty much standard model that you use everywhere. But with Cricking, what makes it special is that you try to make a custom statistical model based on the characteristics of one particular data set. This is all explained in more detail in the handout, including the fact that there are a few different types of Cricking. Cricking can be its own complete course, actually. If you go more into the geosciences, you probably do see it that way, but here we only give a very brief overview to simple Cricking and to ordinary Cricking, which is explained in the handout. Yeah, simple Cricking is a bit too simple to be used in practice, but it gives you the background that you need to understand how the method works. In practice, what you tend to do is ordinary Cricking. Similar to other methods that you saw last week, it's sort of a weighted average method. So if you want to get the value of a particular attribute, let's say the height at a particular point, you compute it as a weighted average of the value of other points, and you assign weights to each point based on the distance to the place that you want to obtain a new value, and these weights should add up to 1. So in this sense, it's very, very similar to other interpolation methods. But we can see what makes it special when we go really to the ordinary Cricking equations, like what you see here in the equation 5.27, which is the way that we compute the weights. The weights here are marked like W1 to Wn, but in order to compute these weights, you need to fill in this big matrix and this vector with the values like that are seen with a gamma. And that's where the variogram comes in, which is the sort of the tricky part of Cricking and what I want to explain to you today. So for that, let's go a bit through the code and how this could be implemented. This is the code that I used for an assignment in the past, and we can go through the steps briefly. Like this just reads the input points and cleans the points by removing duplicates. This is not too important for the computation of the variogram, but when you actually want to do Cricking, if you have duplicate points, it will cause you problems because you end up with singular matrices. So let's just plot one dataset. This is the same dataset that you can see in the book chapter. Here, I think it's a dataset based on elevation in Tasmania. If you look at the points that we get here, you see that there's like a higher part around here, and then there are some lower elevations as you go into the different directions. So you have quite a good number of sample points. They're not evenly distributed. You can see that there are some places where you have points very close together, and actually there are some repeated points in the dataset, and there are also areas where there are not so many points, which can make it a bit tricky to interpolate properly. So if we go through the code, the first thing that you tend to do with the variogram is to view or compute what is called the variogram cloud. This is quite interesting. So you can see that we have a lot of sample points in the previous figure. And if we look at every possible pair of sample points in the data set, you end up with a lot of possible point pairs. Here in the variogram cloud, we're plotting on the x-axis the distance between a pair of points, and on the y-axis it's the square of the difference in elevation. The way that you interpret it is that when you have a distance very close to 0 on the x-axis, the difference in elevation between the points is almost nothing. So nearby points will have very similar elevations, and that goes for a lot of other properties. Like it cannot be only elevation, it could be temperature, it could be any sort of physical property. And as you go farther between the pairs of points, you can see that 2 points that are a bit farther away, they will tend to have a bigger difference in elevations. This reaches sort of a maximum at a certain distance, and then it tends to go down as you go even farther. This might be a bit surprising to you because you might tend to think that the farther you go, there will be like no correlation at all between the elevation, but this is where particular datasets can be a bit tricky. So in the previous figure, we saw that there was a distance of like 250. I'm not sure if it was, I'm not sure about the units there, but so If you go to distances, let's say of over 150 or 200, you are talking about comparing distances basically on the diagonal, like on the extreme endpoints of the area that we're covering. So this gets less reliable as you go. So we can already see some patterns here in the Variogram cloud, but it is hard to actually get some good measurements. So what you usually do is that based on the Variogram cloud, you compute what is called the experimental variogram, where you sort of compute the average dissimilarity between the points. So rather than seeing all possible point pairs here, we compute bins, like we make intervals of distances, let's say every let's say make every 10 units or 20 units to get bins, and then within each bin we compute the mean dissimilarity between the points. And if we plot this mean dissimilarity, we get something that looks a lot cleaner. So we can still see that when there's distance of very close to 0, the dissimilarity between the points is almost nothing. And as we go farther away, then the dissimilarity between the points increases. Usually for this sort of experimental variogram, you only plot it up to something like half the maximum distance between the points, because it's the same thing that we mentioned before, like after some long distance it sort of gets unreliable. But yeah, we can see sort of an increase here that goes off very cleanly, like from very close to 0 to something like what would it be, like 1300. And then the next step that you do once you have these points is that you try to compute theoretical variogram functions. So you create a function that tries to fit these points as well as possible. In the handout we discuss 3 different functions, like an exponential one, a Gaussian, and a spherical one. And if we go here to the section that explains the experimental variogram and the theoretical variogram functions, we see that you usually parametrize them based on 3 different things. These are called the sill, the nugget, and the range, because you expect a similar kind of behavior no matter the function. So there is a nugget, which is sort of the y-intercept. You see very often that the similarities between the points don't really start at 0, but they start at a higher value. This happens a lot when there's noise in the data. So when even nearby points have a certain difference in their measurements. Yeah, like with elevation it's not so common, but if you start measuring, let's say, the example of temperature, and you measure it at different times of the day or with different instruments, you might get different values. So then the nugget will be more than 0. Then there's the sill, which you start at the point of the nugget and you see what is the maximum value that this gamma reaches. Like in this example that we were plotting, it's also like this 1300. And then there's the range, like how long of a distance does it take for you to reach the sill. In this case, we can see that the values start increasing, but maybe after 125 or 150, we see that the value becomes pretty much flat. And that's what you should put for the range. So if we go back to the code here, I didn't fill these values on purpose. But looking at the figure that we have here, we can sort of guess them. Usually you do this by sort of trial and error. You can plot them once, and then you see the values, you plot the function that you get and you see how well they fit, and then maybe you do some adjustments. So we can try to do that here. Yeah, as we said in this example, the nugget seems to be 0 because if you look at the smallest possible value on the y-axis, it's very, very close to 0, which means basically that there's no noise in this dataset, or almost nothing compared to the values that we are actually using. Yeah, then for the range, maybe it is something like 150. So we can put those values there. And for the seal, it might be something like the 1300 that we said. So let's just put this value here. Let me close this plot and just run the Python code again, and we can see what happens. This is the same plot with the different data points. This is the Variogram cloud. One thing I forgot to mention here is that if you're having trouble visualizing every single point pair like I'm doing here, you can always just select, let's say 10% or 1% of the point pairs randomly, and then we will get something that is much easier to plot. And yeah, once we fill in the values that we mentioned previously, we get 3 different things here. So yeah, based on what you can see here, I think we defined the seal pretty well, but the range should be higher for all 3 functions, because yeah, there's still some mild increase once you go yeah, to these higher values. So maybe instead of 150, we can just put 200. And yeah, we can just run this code again and see what happens. Yeah, so it's actually improving, still not perfect. So you could probably still need to define a bigger range for some of the functions. But one thing that we can already start looking at here is that the Gaussian function actually seems to fit much better with this kind of data set. So you can see that the increase in the similarity is sort of very slow at first, then it sort of increases, and then it slows down afterwards. Yeah, so that's also how you choose a specific theoretical variogram function. You see, after deciding good values for the nugget, the seal, and the range, you also decide which function is the one that you're able to fit best, and that's what you use for the gamma values in the Cricking equation. So going back to the book a bit, this is where the gammas that you can see here in the matrices come in. So the gamma of a difference between 2 points, the difference between 2 points, this means like the distance between the 2 points. So you evaluate the gamma function that you defined, which is the theoretical variogram function, using the distance between 2 points. If you see the same point here, it means like basically what is the gamma of 0, so what is the gamma at the nuggets, like what is the nugget value. And here x0 is the point where we want to obtain a measurement. So for every single point that we want to evaluate, we actually need to fill in all of the gamma values here, all of the gamma values here. And since we want to obtain all the weights, what you need to do is actually to do like inversion of the inverse of matrix A, which is this one. Yeah, so you need to be aware a bit, like inverting a matrix is a computationally heavy operation that takes quite a while. So you can imagine that if we want to interpolate at a lot of points, like say you would take a whole raster and you want to obtain the value at every single point on the grid, you will have to, for every single one of those points, fill all of these matrix, fill all of this vector, then invert the A matrix and do this multiplication before you're able to obtain the weights, and that's just to do the interpolation of one single point. So in this sense, yeah, Cricking can be a lot slower than other interpolation methods that you saw last week. But the advantage is that when you're creating this custom statistical model just for one dataset, you're trying to obtain something that's a bit more, that fits actually much better with the dataset. Every dataset is different and it has different characteristics, and you're able to adjust to these characteristics using Cricking. Whereas if you were using something like IDW, then you would just have like the power that you can set, and you can decide maybe I want to use a low power or a high power. Like you saw last week, if you put a very high power, the points that are very far away will have very low weights, but still it's little more than guessing. Whereas in Cricking, you are actually using the properties of the specific dataset, like what is the correlation, like the spatial correlation of the dataset, in order to do the best possible interpolation that you can do. At the end, you should be able to create something that is smooth like this example. But if you want to do something a bit faster, there are some tricks that you can do. These are explained a bit more in the handout, like you can limit your search to some of the points rather than all of the points, which means that these matrices will have a lot, this A matrix will have a lot less, a lot fewer rows and columns. Then the inverting it is going to be a whole lot faster. But yeah, that's basically it about Cricking. Not sure if you have any questions, just you can post something in the chat now. I will be online for a few more minutes if you have any questions. If you need to digest this a little bit, look at the handout, just post it in the Discord text channel later. I'll be happy to have a look. So thank you everyone, and nice meeting you.